We have started, therefore yesterday we started discussion of bond parameters. We have done bond lengths, then bond angles, then bond enthalpy. I told you, if you break a bond between two atoms, it is called diatomic molecules. Then we call this to be, that energy to be bond dissociation enthalpy. And if it is a polyatomic molecule, in that case, we take the average of the bond dissociation enthalpy, and whatever the value that you get, that we call it as bond enthalpy. That is, average of bond dissociation enthalpy is the bond enthalpy. Okay. Then let's see on what the bond dissociation enthalpy depends. Bond dissociation enthalpy depends upon the following factors. Okay. See, I told you, if the bond is longer, then it is easier to break. And if the bond is shorter, it's difficult to break. Then the length of the bond depends upon what? The size of the atom. If the atoms are big and bulky, then the distance between them will be more. And if the atoms are very small, then distance between them is very small. So it depends upon the size of the bonded atoms. Size of the bonded atoms. The smaller the sizes of bonded atoms, shorter is the bond length and stronger is the bond. And stronger is the bond. And larger will be the bond dissociation enthalpy. All right, example. Say we have taken the bond between hydrogen and halogen. We know then halogen, we have four atoms of halogen: fluorine, chlorine, bromine, and iodine. So as you go down the group, the size increases. As the size in that also I've shown you, as the size increases, the distance between the atom increases. And as the distance between the atom increases, you'll find the bond length is going to increase. All right. So if I write here bond enthalpy, I have taken here hydrogen fluoride, hydrogen chloride, hydrogen bromide, and hydrogen iodide. It is having the shortest bond, it is having the longest bond. All right. So in that case, the bond dissociation enthalpy will be HL will be more. So we have to write like this. Okay. Then second, bond length that I already told you now. Depends on the bond length. So I have already mentioned here. So larger the bond length, lesser will be the bond enthalpy. Okay, we'll write here now bond enthalpy. What is the bond dissociation? Third, bond order. I'll discuss to you what is bond order. Bond order is nothing but the number of bonds that you have between the atoms. See, in case of hydrogen, you have only one bond between two hydrogen atoms. So what is this bond order? 1. In case of oxygen, we have already done the Lewis structure. So between two oxygen atoms, we have 2 bonds. So in that case, bond order is 2. In case of nitrogen, there are 3 bonds between 2 nitrogen atoms. So bond order is 3. So as the bond order increases or number of bonds between the atoms increases, they come closer and closer. And in that case, their bond dissociation enthalpy will be, or bond enthalpy will be more. Why? Because in case of hydrogen, you have to break 1 bond. In case of oxygen, you have to break 2 bonds. And in case of nitrogen, you have to break 3 bonds. So what will we write now? Higher the bond order, that they have given you example also. Higher the bond order, more will be the bond enthalpy. So these are the 3 factors which are there. You have to take into account. Okay. So what we can example, what we can write now here. Example is bond enthalpy. Suppose I have written here hydrogen, hydrogen, oxygen, oxygen, nitrogen, nitrogen. So this is bond order will be, bond enthalpy will be like this.
We're done.
Okay. Now I'm going to write down the definition of bond order. What is the bond order? It is the number of bonds between two atoms. Okay. So let me write down here. Molecule hydrogen. What is the bond order? What is the bond order here? 1. Then oxygen. Bond order is 2. Then nitrogen. Bond order is 3.
Sir, done.
Okay. Now I'm going to tell you something. This is important for your exam. That isoelectronic species. It may be what? It may be molecule or ions. Molecules or ions have same bond order. See here. What is the meaning of this? Isolated electronic species, so it may be molecule or ions where they have same number of electrons. See, let me take here fluorine. Fluorine has how many electrons? Atomic number of fluorine is 9. There are two fluorine atoms are there. So 9 plus 9 is 8. Okay. Then I take here now O2, 2 minus. See, oxygen is having 8 electrons. 2 oxygen, 2. And each negative charge is 1 electron. So how many electrons are there? So it is 8. So they will have same order. See here. We know here fluorine molecule is you have single bond between two fluorine atoms. Then what is O2 minus? See, I will write here now O. We know that 2 electrons are required to form a bond between two oxygen atoms. But here this only one pair has formed the bond, other pair did not form the bond. So it remains here. So I'll put one minus sign and one minus sign. Okay? All right. So what is the bond order here? This type of species is called peroxide. What is the bond order here? See, bond order is 1, 1. Okay. Now let me take here N2. N2 nitrogen is 7. So 7 plus 7 is 40. So see here, how do you write nitrogen? What is his bond order? 3. Then let me come here, carbon monoxide. Carbon atomic number is 6. Oxygen is 8. So it is 40. Okay, how does it look like? Bond order 3. Then we have now cyanide minus. Okay, see here, carbon is 6, nitrogen is 7, You have one negative charge means one electron. So it is equal to 40. How to look like? See here. This is this. And the negative charge is here. So bond order is 3. তুমি নেটে কোন দিকে ক্লাস শুরু হয়েছে? হ্যাঁ, তুমি ওখানে ক্লাস কন্ট্রোল দেখেছো? মানে এরকম করতে হবে। এই প্রোগ্রামগুলো না দেখে ওটা দেখা যায় না। এসব কথা বললে খারাপ। এগুলো টাকা দিয়ে দিল। কেন বললে? না তো আমি অন্য বলিনি। Okay. Then we'll come to a very important topic. It's called resonance. See, there are some molecules whose total behavior cannot be explained by a single structure. So, in that case, you have to take the help of multiple structure to explain it. All right? And this phenomenon is called resonance. All right? It is generally observed that a single leaf structure of a molecule cannot correctly explain the properties of the molecule. In such cases, its properties can be described by two or more two or more than two structures. Two or more than the actual structure. Is said to be resonance hybrid of these structures.
Sir, done.
Okay, so let us start with some examples. Say we have taken here ozone. So in case of ozone, the structure that also we have done it through by the leaf structure, and we have determined formal charge also. See here, what is the bond order here? Bond order for this bond is 2 and bond order for this is 1. Okay, so now when we have measured the bond order of this ozone molecule, we did not find a perfect bond order of 2 and perfect bond order of 1. We have got only one type of bond. Okay, where you find we know that the bond length of the single bond is more than that of the double bond. So we have got on one type of bond length where we find that it is lies in between 2 and 1. How it is possible? Then we find that this is having a structure of it is the double bond is migrating. If it is first oxygen, second and third, so for between first and second it goes to second and third, like this. These electrons are migrating. So in that case, what we can write? We can write the actual is the hybrid is which is migrating between this oxygen and this oxygen. So in that case, we find that it is neither a single bond or a double bond. It lies in between two. So that is the resonance hybrid of ozone.
Sir,
Yes.
sir, I did not understand this. Can you explain again?
Which one? See,
Sir,
this is the
resonance.
new structure of ozone. Just see, that I have drawn it now. Oxygen, oxygen, oxygen. Oxygen has 6 valential electrons. All right. So this is 6. So here See here. These are the 6 electrons of this oxygen. These are the 6 electrons of this oxygen, and these are the 6 electrons of this oxygen. Now I count. See here. 4 plus 4, 8. Then 4 plus 2 plus 2, 8. Then 6 plus 2, 8. So this is the structure. See here. This is the structure. Double bond we have. And this is the coordinate bond you are having it. See, then in that case, this bond order of this oxygen is 2, and this is 1. But when we have done the experimentally, when you determine the bond length with the help of X-ray machine, we find no, it does not show a perfect double bond or a perfect single bond. It lies in between two. That is, the bonds are migrating. How the bond can migrate? Bond is being formed by electrons, so electrons are migrating from one place to another. All right. Now, in that case, I can draw this structure. I can show you the migration of electron. How generally we show it in our chemistry? We show it like this. See here. This is a lone pair. So when 2 electrons are on the same atom, we call it lone pair. But we know if these electrons move to the neighboring atom, then they can form a bond. They can form the bond. So here, one of the electron has gone to the oxygen, immediately a bond is being formed. But in all the cases, this oxygen should maintain octet. See here, how many electrons are there? 8. Moment one of the electron from here goes to this orbit, it becomes 9. So one of these electron has to migrate. Sorry. So what will happen now? As the electron has come here, it becomes 9. So you have 1 electron here and 1 electron here. So immediately this electron will come to the oxygen. See here now, count. How many are there? 2, 2, 2, 2. This electron belongs to this oxygen. So this is the one. This electron from oxygen has come. Why it has to come? Because this oxygen has received another electron from the neighboring atom. All right. So now see. So this migration of the electron takes place. And this is a continuous process. It does not stop. Once you get this one, again this electron will go and will come back. So it is a continuous process. Because of that, I have given a double-headed arrow. So this is being shown. See, this is the hybrid. It shows you do not have any solid bond between any two atoms. So this migration of electron is being shown by this structure. We call this to be resonance hybrid. Otherwise, if you have taken this structure or this structure also shows oxygen-oxygen have double bond and oxygen-oxygen single bond. If you have taken this structure also, it shows oxygen double bond and oxygen-oxygen single bond. But we do not get a perfect single and double bond. It lies between two. That I can show only by this structure.
Sir,
Yes.
so this migration takes place only for those molecules where the bond order is not perfect, or for all molecules?
No. You cannot say like this. I told you that if you want to interpret its total behavior, then only all molecules do not show resonance. There are some molecules whose all the properties cannot be interpreted by only single structure. All right. So in that case, you have to take the help of the more than one structure. See, the behavior of a particular person cannot be explained if you see him in one place. If you see him in different places, if you find it is always same, then you can interpret. But you find going to the different places, his attitude and his behavior is changing. Then only you can explain that this is his true behavior. Now, let me take the example of carbonate. That also I have shown you the new structure. What is the structure of carbonate? See here. Carbonate, this is the structure of carbonate. Here I will put a negative charge because 2 electrons are added from outside. So here also, bond order of this is 2, this is 1, and this is 1. All right. Again, here when we have taken the X-ray of this molecule, we did not find any perfect carbon-oxygen double bond and carbon-oxygen single bond. Only got only one type of bond. Then how it is possible? See here in this case, what will happen now in this case? So it is 1, and this is 2, and this is 3. What will happen now? See, this electron is coming. So, see here. Here you have one electron, here you have one. Clear? The moment this comes, then this carbon will have 9 electrons. How? See, this is one electron, this is one electron, this is one electron, this is one electron. See here, how many electrons are there? 4 plus 2 plus 2, 8. So moment this electron comes, this electron will migrate. So now what will have now here? See, the structure that I am going to draw. This pair I have written it here. This is this pair. This electron belongs to oxygen only. This is here, and this is the electron, the carbon, which was initially the carbon. As the carbon has got one electron from outside, it can give its own electron. See here. Now what we have? See? I write down here one negative charge. Why? Because this carbon has got an electron from this oxygen has got an electron from carbon. It initially did not belong to. So okay, now see here. So the double bond was here. Now it has migrated here. Now what is going to happen? See here again. So you will get a structure. See. So we find the continuously double bond is moving from one place to another. And these are not rigid. See again what will happen now? This will come. Okay, sorry, this will come, this will go. You will get this structure. Then this will come, this way it will come, this will go. You will again get this structure. Alright. So these are interconvertible. Alright. So in that case, what we can write now? What is the hybrid structure? See, this is the way electron is migrating. So this is the resonance hybrid. So when you have taken the help of this resonance hybrid, all right, then only you can interpret why carbon dioxide does not show a perfect carbon-carbon double bond and perfect carbon-oxygen single bond, because it exists in this way. In fact, resonance is a imaginary. Resonance is imaginary because you can never isolate these structures. So we can interpret only through this concept. So resonance is not a reality. It is an imaginary way of explaining the behavior of a certain molecule or a ionic species. Okay, though it is imaginary, though we cannot isolate, but in all different reactions in the when you interpret the physical properties and chemical properties, you'll find that resonance hybrid really explains the true property, but we cannot isolate them.
Sir,
We cannot. Yes.
can you explain this again?
See, this is the theoretical explanation of the perfect behavior of a molecule, where you find a single structure does not help us to explain its total behavior. All right. So it is a theoretical. So you cannot isolate this structure, you cannot isolate this structure, you cannot isolate these structures. But you also cannot interpret the total behavior of carbonate. Huh? You cannot interpret total behavior if you don't take this into consideration. So it is imaginary. Resonance is an imaginary concept to explain the true behavior of a molecule.
Sir, I did not understand that migration parts. I did not understand
Yes.
properly.
No. If this structure is rigid, when you take the X-ray of the molecule, how many carbon-oxygen single bonds you should see? 1 and 2. And you will get carbon-oxygen double bond 1. So you have 2 carbon-oxygen single bond and you will have carbon-oxygen double bond. Carbon-oxygen single bonds, we know that lesser the bond order, higher is the bond length. So this bond length should have been more and this bond length should be less. So in X-ray, we should have got 2 types of carbon-oxygen bond length, 2 types. But why do you see only 1? Why? There should be some interpretation or not? Okay. How to interpret? Can you see a molecule? See, suppose I told you, if you want to interpret the total behavior of a person, then whatever he is doing, you are observing it. If possible, you can different activities of the person. You can even you can record it, and you can show people that though you thought the people is good, but actually see this is the bad thing he is doing it. Why? Because you have evidential proof. Can you see these molecules? Molecules are not visible. Atoms are not visible. Okay, but when you take the X-ray, we find we have only one type of carbon-oxygen bond length. And we know bond length depends upon their bond order. So whatever the carbon-oxygen bond we can have, see there are so many molecules are there where you can have carbon-oxygen bond and these bonds are rigid. So you have calculated, but that does not fit it here. Because we find the actual bond length of carbon-oxygen bond, whatever we got from other molecules, this is smaller than that. And carbon-oxygen double bond also we know, and we found in that case, this carbon-oxygen double bond length is more than that. So it is only possible if we take the help of this structure. But how will you come to this structure? There should be a logical conclusion. A logical conclusion should be there. So how can you come? We can come, first of all, we show that these are the different ways that carbon-oxygen double bond migrates from one oxygen to the other. And how? Formation and breaking of the bonds only takes place through the movement or shifting of electrons. So we have shown that from this oxygen, one electron is shifted here to form a double bond. And as because we have to follow the octet rule, I've shown you that this each and every atom here in this having the octet. So moment you supply one extra electron to the neighboring atom, then it becomes 9. So the neighboring atom will push his own electron outside to accommodate it. See here now, it is 4 plus 4 is 8. Here it is 6 plus 2 is 8. Here it is 6 plus 2 is 8. So as one of the electron is coming to this carbon, in that case, when it is coming to this carbon, it becomes 9. You count it becomes 9. All right. So it pushes this electron to the nearing oxygen. So this is the structure I have drawn. Did you draw the structure?
Yes, sir.
Yes, sir.
See, this is benzene. This is benzene. All right. Generally, we don't write the carbon there. This is benzene. See here, every carbon is having octet because every bond has 2 electrons. Take the example of this carbon. See here, 2. In this bond you have 2 electrons. In this bond you have 2 electrons. 2 plus 2, 4. Then you have this. Then you have a 2. Okay, 6. And this double bond is also having 2. So 8 electrons are there. So this is benzene. So generally, we don't draw the benzene in this. We don't draw the hydrogen because organic compound is made up of carbon. So this is one. See, suppose my label is 1, 2, 3, 5, 6. So you have now carbon-carbon double bond between 1 and 2, 3 and 4, and 5 and 6. Then carbon-carbon single bond. Then you have between 2, 3.
Excuse me, sir.
Yes. Hello.
Sir, can you please repeat it again?
No, I will explain. Yes.
Sir,
Which
can you
one I
please
put it?
repeat it again?
This one.
This one, sir, the first one. Yes, sir.
No, I'm telling you. Let me write it. 4 and 5 and 6 and 1. See, this is benzene. Benzene formula is C6H6. This is the structure of benzene. All right, but we generally draw the benzene without hydrogen and without carbon. See, this is benzene. This is the benzene. But when you draw the benzene, we don't write carbon and we don't write hydrogen. Could you understand now? Huh? When you draw the structure of benzene, we do not write carbon and hydrogen because we know organic compounds are made of carbon and hydrogen. Understood? So in this structure, what you have? You have carbon-carbon double bond between first and second carbon. Don't write. Then third and fourth carbon. Then between fifth and sixth carbon. And single bond you have between second and third carbon, fourth and fifth carbon, and sixth and first carbon. All right. So when we have done, see. So what is the bond length? We find that carbon-carbon bond length is 154 picometer. Carbon-carbon double bond length between carbon-carbon this and between 132 picometer. So when X-ray of benzene was taken. Only one type of carbon-carbon bond length was observed. You know how much? 140 picometers. So, this is the reality. This is the structure that we have drawn. There is nothing wrong with the structure. Then why this change has taken place? It should have showed two types of bond length. Why it is showing only one? These structures are not rigid. Continuously some change is taking place within the carbon, and whatever we are getting it is the average structure. It is the average structure. All right. So, people, there is another structure is being proposed. Sorry. Another structure is proposed. It is 1, 2, 3, 4, 5, 6. It is now see here, wherever you had double bond, we are having single bond. And wherever single bond we had, we have double bond. Then also it does not explain us. Why? Because if you can separate them, in chemistry, the separation technique is there. We separate so many things from a mixture. So in that case, if I separate them, again, they should show us the same thing. You can say that, sir, it is a mixture of between this structure and this structure. Because of that, we are getting average. So it is not a simple mathematics. If you separate them, then again they should follow this. But we find that we cannot separate. Benzene does not have any separate structures. Then what should you say? We should say this structure is continuously changing to this structure, and this structure is getting into these structures. So ultimately, we get a average structures where you find the electrons are continuously moving. They are not rigid. All right, and that is the one that we can help it with, to explain it only through resonance. All right, please write. Then I'll.
Sir, done.
Wait.
আর মূলধন তো বলছি না, ওগুলো বলে তো চাল দিয়ে করবে, বুঝছো?
It is the electron must move. In this case, which electron will move? Electron, outside bonds electron will not move, because outside bond, if the electron moves, the molecule is going to break. See here, these are the electrons which is inside. So now, this electron is going to move to this carbon. I told you that here each carbon in benzene is having octet. I showed you. So this electron will come to this carbon. every electron carries a negative charge. See here. As this electron has come from this carbon to this carbon, so in that case, we have to put a positive charge because loss of electron is being indicated by a positive sign. And gain of electron is being shown by a negative charge. Just come here. Now, this electron is not rigid, it is moving. Now this electron, see here I told you again, moment this electron comes here, then in that case, okay. First I need to show you this one. Don't get nervous. This electron belongs to this carbon. Okay? This electron belongs to this carbon. So it has come here. This electron does not belong to this carbon. So I have to, whenever an electron from the neighboring atom comes, we have to show with a negative sign. So because of that, I'm showing a negative sign. Okay. Now, this electron is now moving to this carbon. Moment this electron moves to this carbon, then this electron will move. Why? Because in that case, it is going to cross octet. And this electron will come here. All right? I told you, two electrons on the same carbon, so the same atom, we call it lone pair. And two electrons on the adjacent atom, it forms a bond. See here. So what you are going to get here? You get a bond here. Plus, this is the negative charge. Why? Because this electron has, this is the electron of this carbon, and this is the electron of which has come from here. So to indicate this, we put a negative sign. We never show with dot. All right. Now, this electron again migrates. When it migrates, this electron again will come here. So what you will get now here? You will get it. The structure becomes this. And this is the one. Finally, its journey is over. It will go and form the structure. And after that, continuously this type of electron movement is taking place. Okay, this process is called delocalization. If the electrons are present in on a fixed atom permanently, we call them as localized or lone pair. And if they continuously move from one place to another, it is they are getting dislocated from their place, so we call them as delocalization. So resonance is nothing but the delocalization of electrons. See here, continuously this is moving. It's not necessarily its journey will stop here. No. Again, what will happen? Again, it will come in this way. You will get this structure. This will come this way. You get this structure. This will move, again this will go. You get this structure. Again this will go. So because of that, we're showing with double hydrogen. So ultimately, what I can show here? Okay, we'll show that this type of a current of electrons going inside the benzene ring. So this is his resonance component. Resonance. Now see, can you say here? Can you say that any fifth double bond is there? No. This is the resonance hybrid. You will find in your book Many places they given the benzene in this way. It interprets the benzene does not have a fixed carbon-carbon single bond and a carbon-carbon double bond. So we write this is equivalent to this structure. So this is the resonance structure of benzene. So what precaution you should take? You never move your arrow from the bond outside. You have to move this bond from inside. This I'll tell you later on. What are these two bonds are there? The outside bond is called sigma bond, and this is called pi bond. That I'll explain later on. All right. So this is the resonance structure of benzene. Okay, these structures of resonance are called. This is between the structures, whatever the structures we have, is 1, 2, 3. These structures are called canonical structure. So these canonical structures is our imagination. Otherwise, we cannot interpret the other structure of this benzene, how it is being achieved. Okay, they are called canonical structure, and these canonical structures have no real existences.
Sir, done.
You have done. Please draw the structure
Yes,
again. Again you draw, because often you have to draw this structure and exactly draw the way I have drawn.
সুরের সাথে আমি বলছিলাম তোর অফিসে তো মেয়েদের ফাইল থাকে এটা বাতনা দিতে পারলে
তুমি তো কারণ আছে আর পর
বলেছি
কই দিয়ে আসো
বলেছি
জানো না
দেখতে বলেছিলাম করতে বলি দেখতে পারলে আমি তো একটা নিয়মটা নাই করছি আমি বলেছি বলে তুমি করছো না বিষয় আইসবে তো দেখেছি দেখে বলে করবে করেন দেখতে
The canonical structures have no real existence.
chapter center.
See what is the meaning of this? We have done totally from first to the last chapter. There are 5 structures. Okay. You cannot say that on first, second, the first structure is second, the second structure is third, the third structure. You cannot say like this. Okay, it's totally imaginary. There is no equilibrium. Between the various canonical forms.
Sir,
Yes, please
sir,
tell.
on that chemistry chapter 3, sir. Sir, the elements which are having atomic number of above 100, sir, which name do we need to remember, sir? The nomenclature name or the other name?
Okay. I'm going to tell you. But actually, you know, though this question is being given to us, you told me, but now all the elements are being deep. Anyway, I am telling you. See, thing is that maybe a same element is being discovered in different laboratories in different countries, or maybe in the same country. See, everybody wants to give a name. Just like that, in different houses, the children are born. Parents or grandparents or anyone, they name their children, and that name goes. But the difference between element and the children is that all children are different, but elements are same. Okay, in that case, it is not that suppose American is a very strong country. America has put a name, and suppose India has put another name. In that case, it's not that the American lobby will be strong or not. It is not like this. One body is there. We call it IUPAC. IUPAC. International Union of Pure and Applied Chemistry. Okay. So the different laboratories or different scientists, they discover the elements and they study their properties and everything, and they send this to IUPAC. IUPAC has a tradition of looking into the correction, keeping new names of the molecules, everything after a gap of 10 years. All right. Then what will happen to this element whose all the compounds are being prepared and everything, how people are going to name it. So within 10 years, that some way the elements, properties of the elements and compound should be, formula should be written. So in that case, what we do, we name the element by their atomic number. And the numbers are being taken from the Greek, because all our scientific names and everything initially started from the Greek or Latin. All right. So it is being named after this. So 1 is called un, 2 is called bi, 3 is called tri, 4 is called quad, 5 is called pent, 6 is called hex, 7 is called hept, 8 is called oct, 9 is called non. Okay? And 0 is called nil. So we name them in order of their atomic number. And by convention, most of these elements' name ends with I, U. See, potassium, sodium, like this. Huh? So in that case, suppose the atomic number is 100. So what we are going to write? For 1, we'll write un. For 0, we'll write nil. Okay? Then for again 0 is nil. Un plus nil plus nil plus IUE. What we are going to name, we'll write now? Un nil. Nil. Understood? If it is 101, so we'll write as un nil un plus I. So what we'll call it? Un nil unya. Okay? Suppose it is 119. This much has not done till now. Say it is 115. So it will be un nil PNT I. So we'll write now here. Yes.
So it should be un pentium, right? Because 1 is there.
Oh yes. Correct. So we'll call it. First will be alphabet. Un pentium. Understood now? So
Yes,
this is
sir.
the way we write it. Right now. Now all these elements are now named.
Sir,
Yes.
so like suppose for that element number 104, sir, which name do we need to give, sir? The Rutherfordium or this name, sir?
No, in your textbook, as they have, I don't know whether they have given you the latest book, all the names are being given. If it is not being given, then you will write Undil Quadium.
Okay, sir.
Wait. Let me find the book. From 101 from 100, the Can I rub it?
Sir,
Yes, sir.
The book which I have taken is published, I don't have the latest book, 2012. Now it is 2020, na? So latest book in your textbook you will find. I think your textbook is the latest one. You can find out there. Atomic number and name. Is there in your book also? Earlier it was called unilinium. Now this is called fermium. Fermium has come from a name of a very famous person from physics. Okay. His name is Fermi. Then 101. Okay. The symbol is FM. Then is being named after Mendeleev. Mendeleev, MD. 102 is being named after Alfred Nobel. Nobelium. NO. Then 103 Lawrencium. LR. Lawrence, he has done a lot of work in the inner tensional elements. 104, we call it Rutherfordium. RF. Rutherford, you know already.
101. Name.
Mendeleev. Mendeleev. Then 105 is called Dubnia. I do not know, is a man from physics or chemistry. DB. 106 is called Siborgia. He is a person from earlier all these persons used to work both in chemistry and physics. Siborgia. SG. 107 is called Bohrium. You know who is the Bohr? Bohr is Niels Bohr. Both Bohr and his son, both of them are being awarded Nobel Prize separately. Okay. 108 is Hassium. He has done a lot of work on periodic table. HS. 109 is called Methnerium. NERIUM. MT. 1010 is Down Stadium. BRMSTA D TIUM. Darmstadt. This is the name of a place in West Germany. So, no, Germany. Then 111, you know the name of this person name you have already heard, is called Röntgenium. Do you know who is Röntgen? Hello?
No, sir.
He is the person who has discovered X-ray. Now 112 till 118. In latest book, the names will be there. All right. In my book, it is not there. It's an old book. So this is called now own biome 113, own triumph 114, own quadium 115, own pentium 116, own hexium, then 117, own heptium, and 118 is own octium. All right, but now all these elements are named.
Sir,
Yes.
so what is the electronic configuration of copper?
We have already done it. It is 1s2, 2s2, 2p6, then 3s2, 3p6, 4s2, 4s1, 3d10. Let me find the latest periodic table. Name I could find. It's called copper NiCium. Some symbol is Cn. Okay. So this name is being derived from a astrophysicist. The first astrophysicist that we have come across in our in astronomy is Copernicus. Is being named after him. Others I do not know.
So
Yes.
just now, no, you said that the element from 112 till the
Mhm.
element of 118 are what, sir?
112 is called Copernicium.
Okay.
Copernicium. Is named after Copernicus.
Okay, sir.
See, initial two persons who have done prove that. So Galileo Galilei, he has proved that the Earth is moving around the sun, and after that he was being pushed to death by the clergy people. Okay, and another person who has done this a lot of work initially is Copernicus. So it is being named after Copernicus. And other, if you go for the latest periodic table, you go for the Google, you'll find most of them are being named. Okay, so well, anyway, so now some of you have already asked me that your miss has told to write this electronic configuration in this way. Say, take the example of copper. Copper is it is 29. So 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 and 4s1 and 3d10. But your miss has told, I don't know from Anthony or some other school, maybe in BSF also, it is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s1. It is given in your book also, and your miss also told you to write. See, I told you to write like this, and in your book is given like this, and your miss also told. All right? Huh? See here. Whatever this electronic configuration that I have written, I did not write of his own. I'm not a master. I have only followed the energy principle of filling up of the electrons. And that energy principle depends upon a very famous law. It's called Bohr-Baris law. And on the basis of that, we always write this diagram. All right? So if your miss has told you right, I have nothing to tell. Because when you fill up the electron, you fill up it like this. But we know very well, the energy of the 4s is lower than that of 3d. So you, in your book also is given like this. I have nothing to say.
Sir.
Yes.
Sir, from chapter 3, sir, that last part, sir, we haven't done right, the periodicity in chemical properties.
I will not do it. I told you. When you do not know anything about the chemical compound, then how can I explain it to you?
Yes, sir.
I did not go to the Mars. Can I explain the surface area of the Mars? Let us try to know this compound, then only I can explain. All right?
Sir,
There are
then
so many
we'll do it later.
Yeah, we'll do it later. Why not?
Okay, sir.
Everything there in the book, I'm going to do it for you. Okay? And I told you that science is not a matter to by heart. If anyone tells you you by heart it, then you should know this person has studied science by force. A flower which you have not seen, can you explain its beauty?
No, sir.
Then okay, bye.
Sir,